Hello. It's Friday. So
Absolutely.
a time for a drink and some science.
Science.
Hi, I'm Dr. Lex.
And I'm Dr. Demos.
We're the hosts of the podcast Luxi, and this is our little YouTube series where we have a cocktail and talk about something cool from the week in the world of science. And
Yes.
this week, we don't have a cocktail. We have some champagne because we managed to make some inroads into getting some, what do you call them? Not really errands.
Yeah, Greek bureaucracy. Figuring it out.
Yes.
But it's been an important week in science because Nobel Prize week.
It is Nobel Prize week. You know, I have personally boycotted the Oscars for years until they televised the Nobel Prize ceremony.
There you
It's
go.
my own personal objection.
You're a true science.
I would love to see it. Wouldn't you? It'd be so
I think
cool.
it would be fun. I think there needs to be some drama and spectacle. And there should be, I think you would enjoy the runway fashion.
There's a legit European royalty there. There's got to be some good gowns.
Good gowns.
Anyway, so the Nobel Prize for Chemistry was announced recently. It was announced for 3 people, 2 men and a woman being still fairly rare. And for one of the men, Dr. Sharpless, he's one of only 5 people to have won 2 Nobel Prizes.
Oh, wow.
Yeah, pretty cool. But they invented something called click chemistry.
And click chemistry is?
Kind of like Legos with molecules.
Oh, wow, amazing.
Did you take organic chemistry in
Yeah, but
college?
I've forgotten everything about it.
Yeah, but did you have that little kit where you'd like pop an atom on?
Yeah.
Pop an atom on.
Yeah, it
and
was
then
like Legos.
Yeah, and then you'd be in the exam and all you hear is pop, 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 pop.
Yeah, it was pretty annoying.
Yes, sort of like that, except not with the individual atoms, with the whole molecule, right? And the idea is to simplify the process of getting molecules to bond together. And that has advantages in drug discovery for making that faster. And the way they did this is they wanted to harness a natural bond that already happens. So they did it with a group that contains a nitrogen ion, another group that contains a triple bond of carbon. And they found that if you add copper as a catalyst, this bond happens very quickly. Okay. It's a very strong bond. The advantage is you can kind of carry something else along with it. So it's kind of like a Lego, right? You can kind of attach infinite numbers of Legos on top.
But you have to have copper to make them stick together.
You have to have copper to make them stick
together.
together.
But copper, you say, is also toxic.
Right, and so this is where Carolyn Bertozzi's research came in handy. So she was working on something completely different. She was working on glycans, which are found throughout your body.
Okay.
Kind of like sugars, long polymers of carbon.
Okay.
And we don't know much about them or what they do. We do know they're important for certain processes. So she wanted to study them in cells. So she's like, great, there's this thing called click chemistry. I can click a fluorophore onto my glycan, and then when
fluorophore being something that glows in the dark.
Well, glows when excited by a laser.
Okay.
So she's like, but I can't use that technology because I can't have copper as a catalyst because that is toxic to living cells. And so she figured out a way to manipulate one of the molecules in that reaction I talked about. And that acted as sort of its own catalyst. And then she can attach a fluorophore to the glycans and be able to study what these molecules are doing in human cells and sort of map the route through the cell by exciting them with lasers.
So did she get then the research was awarded a Nobel Prize because of the ability to avoid using copper as a catalyst?
Yes.
That's amazing.
Yeah, so it's one of those nice stories where people sort of built on each other's research, right?
Wow.
Like these 2 men came up with click chemistry initially, and then she took that concept that was fairly widely known and adapted it for a more biological use.
Wow.
Yeah.
So a Nobel Prize for the omission of an ingredient.
Yeah, it might be the first one. Who knows?
Wow. You figure someone needs to get a Nobel Prize for a flourless chocolate cake.
I don't like flourless chocolate cake. It's too dense for me.
More chocolate is better. Well, my area of interest was based on a conversation I had with some friends or ex-coworkers from my company who went on to work for some interesting groups like Helion Energy.
Helion.
So Helion's a great name. It means it's a Greek name for sun. helium.
So is it solar power?
No. Interestingly enough, it's a company that's doing research on hydrogen fusion.
Hydrogen fusion.
So, in this talk of an energy society that's needs energy for everything, we're talking about the potential to create truly portable fusion generators, and
Like-
that we're actually close to actually making them work.
How portable?
Portable enough to put on a kitchen table.
Really?
Yeah.
Well, that's very interesting. And what advantages would fusion have over, say, fission, which is what nuclear power is at the moment?
So with fission, what happens is you take an activated or a very energetic radioactive particle that is unstable, and you create a situation, a criticality, where an unstable element like uranium-238 comes in contact with enough other uranium and neutrons and reflection of neutrons that you get to a point where the amount of energy and neutrons, it's like a vat of boiling water, but it's a boiling molecular or elemental soup, and you have an explosion and a disruption of those molecules, and you degrade to a different molecule like uranium-235. So that result of that molecule disintegrating, if you will, in its own soup of neutrons and other radiation, it would yield an enormous amount of energy.
Right.
But it's a messy process. It's an extremely messy process, nuclear fusion, and it creates a lot of other radioactive daughters, not just going from uranium-238 to 235, but you also get strontium and calcium and iodine, and they're all radioactive too, and it's a result of this. So instead of dealing with this messy, almost a junkyard of elements, what if you just had the two cleanest elements that you could find on the periodic table, helium and hydrogen?
Also very explosive.
Exactly, very explosive, but not on their own. They are only explosive in the presence of oxygen. So you have an oxygen-free environment, and you create an extremely high temperature plasma of helium and hydrogen, and then you accelerate this high temperature plasma using magnets. And because plasma, in its form, this glowing orb of material, has a lot of energy to it. Like steam has a lot of energy when you boil water. Imagine taking now this and then accelerating it down a cone, and as the acceleration happens, this ball of plasma gets tighter and tighter and tighter and tighter. And then it's accelerated and it meets another ball of plasma from the other side of this cone, two cones facing each other. So we're squeezing these balls of plasma, we're adding more energy to them, and then we're accelerating them, and then they hit each other. And the result of these two extremely high temperature balls of plasma having a collision results in a brief period of nuclear fusion.
Okay.
Yeah. So
How close do you think they're?
they said they're a year away from having a nuclear fusion system that operates once a second.
So if you had a kitchen countertop nuclear fusion reactor, how much power could that produce?
The fascinating thing is something of that size could easily produce 1 million watts.
So like, what does that translate into in terms of powering things? I have no
Great.
concept of what 1 million watts can do.
Well, it's a house with, let's say, air conditioning running, charging an electric car, maybe doing a couple loads of laundry. It's just 10,000 watts.
Right.
So then 1 million watts, 1 e to the 6, 1 e to the 4, 200 houses.
Right, it's not bad.
So imagine 200 houses. Now, the number could be a lot higher than that, and the technology from Helion Energy is interesting in that it doesn't have the waste heat isn't used to boil water to run a turbine or something like that.
Turbine, yeah.
All of the energy that is collected from this fusion is collected from the hot plasma and the magnetic field it generates. So when the hot plasma has the fusion explosion, it creates a new magnetic field that repels the old one. And capturing that new magnetic field energy is essentially like slowing down a runaway train. If you have the brakes around the runaway train and you can slow it down, you can capture that energy and put it back into a power grid. The key though is it only runs once a second, so it'd be a pulse of energy and then nothing, then another pulse of energy and then nothing. So coming up with a way to smooth that energy trough out would be the thing.
Oh, cool. Well, I guess we'll just watch this space then, see what happens.
Yeah, it's pretty fascinating. So Helion Energy has an excellent website. It's worth going to. They're spelled with an H and an E, like helium.
Yeah.
But yeah, check it out.
All right. Well, I'm going to finish my drink.
As will I. And
well, we hope you have a wonderful weekend, and join us here next week for another cocktail and another little bit of science.
Absolutely. Thanks for being part of it.
Cheers.